All right, class. So now we're going to move on from the naming of alcohols and ethers, and we're going to move on to the properties of alcohols and ethers. And the first thing we're going to talk about, or the first property that we're going to go over, is the boiling point of alcohols and ethers. So before we go on, there's just three things to consider, or there's some things to consider in terms of things that affect the boiling point of a compound. The first thing that affects the boiling point of a compound is its size. If you're comparing molecules that have all the same functional groups, the bigger the molecule, the higher its boiling point. The next thing that affects the boiling point of a molecule is surface area. So the more surface area a molecule has, the more that it can interact with another molecule of itself, and the higher its boiling point. So straight chain alkanes, they have higher boiling points than branched chain alkanes. And then the third thing that comes into play in terms of determining the boiling point of the molecule are the intermolecular forces that are at play. So remember, when you have molecules, we can think about the intra. So when we think about forces, we can have intra, I-N-T-R-A, and inter, I-N-T-E-R. So intramolecular forces, those are within a molecule. All right, so these are forces within a molecule. So these are things like covalent bonding, ionic bonding, the things that hold molecules together. Intermolecular forces are forces between different molecules. And when we're talking about intermolecular forces, there's a ranking of them. So the stronger the intermolecular force, the higher the boiling point associated with the molecule. So the strongest intermolecular forces you can have between two molecules are what we call ion-ion interactions. And then as we go down the list, we start becoming less ionic. So we can have ion dipole, we can have dipole dipole, and as a subset of dipole dipole, we can have the strongest of the dipole dipole interactions are what we call hydrogen bonding. All right, and then we have dipole induced dipole. So this is between a polar and a nonpolar molecule. And then at the very bottom, we have the van der Waals, which are completely nonpolar molecules. So these are two ions interacting. This is an ion interacting with a polar molecule. These are two polar molecules interacting. The strongest of that type are what we call hydrogen bonding. Then we have a polar molecule interacting with a nonpolar molecule. Then we have nonpolar molecules. So the stronger the intermolecular force, the higher the boiling point. So if you look at the molecules I have listed here, so what I'm asking you to do now is to try to rank the boiling points of these. And you can go from highest to lowest or lowest to highest. But just rank these in terms of their boiling point from lowest to highest. Keeping in mind that, so all of these are going to have, we're basically not going to worry about size and surface area because all of these have different functional groups. And what we're going to focus on are the intermolecular forces. So see if you can think about which one has the strongest intermolecular forces, and those are in turn going to have the highest boiling point. So pause the video and try to do that. So welcome back. So hopefully you tried to give that a go. And as you can see, what you find is that the more nonpolar a molecule is, the lower its boiling point. All of these molecules now they definitely differ in their molar mass, but if you just kind of are looking at kind of like the number of atoms involved in a molecule, they all have roughly the same number of atoms, okay? And what we're really looking at are the intermolecular forces at play. So this is a nonpolar molecule, so it's going to have the weakest intermolecular force, so it has the lowest boiling point. And then as you move up the list, what we find is that the more polar the molecule, the more dipole-dipole the molecule is, and the stronger the dipole-dipole interaction and the higher the boiling point. So this molecule is a little bit less polar than this molecule because chlorine's more electronegative than oxygen. So this is going to have the next, so you go lowest to next lowest, and then between these two, even though the chlorine is more electronegative, this molecule can take part in hydrogen bonding. And that is the strongest of the dipole-dipole interactions. And this is kind of how that hydrogen bonding network takes place. So the oxygen's partially negative, the hydrogen's partially positive. So this partially negative oxygen can kind of connect to a partially positive hydrogen, and you see this kind of network of hydrogen bonding taking place through the molecule. We see the same thing when we look at aromatic rings versus phenol, so benzene versus phenol. Again, this molecule is bigger and it can take part in hydrogen bonding, so it's going to have a higher boiling point. So boiling point, remember, size, if all the functional groups that you're comparing between molecules are the same, you're looking for the biggest molecule with the most surface area. But if you're comparing different functional groups, then what you need to start thinking about are the intermolecular forces that are at play. The stronger the intermolecular force, the higher the boiling point. So one of the things that we're going to move on to now is we're going to start talking about the acidity and basicity of alcohols and phenols. And so one of the things to think about is how would you classify an alcohol? Would you classify an alcohol as acidic / electrophilic, basic / nucleophilic, or both? So take a minute and just think about how you would classify an alcohol. And really, you know, we're throwing in terms electrophilic and nucleophilic, but I want you to focus on acid, base, or both. So would you classify an alcohol as an acid, a base, or could it be both? All right, welcome back. So that's a weird question, or I mean, it's not a weird question, but what determines whether a molecule is going to act as an acid or base is kind of where the partial charges are. And again, oxygen's more electronegative than the carbon and the hydrogen, so it's going to be partially negative. That's going to make the hydrogen partially positive and the carbon partially positive. Anytime you put a partial positive on a hydrogen, so this hydrogen will be partially positive, this oxygen will be partially negative. Anytime you put this partial positive on a hydrogen, that makes that hydrogen acidic. All right, so alcohols can act as acids, but we also are putting this partial negative charge on the oxygen. So the oxygen can act as a base. So it turns out that alcohols are both acidic and basic, and they're weak acids and weak bases. So alcohols are weak acids and weak bases. And it really depends upon what you're reacting it with. So for example, if you take an alcohol and you react it with something that's more acidic than this proton, the oxygen will do a proton transfer. The oxygen, which is partially negative, will attack the partially positive hydrogen. So remember, when we're talking about these partial charges, oxygen is more electronegative than the hydrogen, partially negative, partially positive, partially positive, partially negative. The halogen's a good leaving group. We know that from SN2 reactions. So because this hydrogen is more acidic than this hydrogen, this oxygen will donate its electrons in a proton transfer process, and you make the oxonium, the protonated version of the oxygen. So we've seen this numerous times. And the same thing happens with the phenol. But we can also use, the alcohol can also act as an acid. If I use something that is more basic, then I can make the alkoxide anion. But what's shown here is actually water removing the proton. And this reaction, water's not quite basic enough to remove this proton here. The equilibrium still lies well on this side of the reaction. But this is just to illustrate that how the alcohol can act as an acid. So if I use something basic, I can remove this partially positive proton, partially positive, partially negative, to make the alkoxide, the O minus. Okay? And the same thing we see with the phenoxide anion. And again, we'll go over the acidity of these things and how they rate. Now, what we want to think about is we want to be able to look at something and think about if you want to kind of compare things, and we want to try to determine when things are very acidic or not as acidic. So when we think about acidity, we want to go back to this Ka equation. So remember, the Ka is the equilibrium constant for an acid-base reaction shown below, and The higher the Ka, the more acidic. And remember, Ka and pKa are kind of inversely related. So this equation right here is telling you the more acidic this is, the more of this you make, right? So that's how, remember that's how all this is working. So this Ka equation, the more acidic HA is, the more of this you make. The bigger this numerator gets, the bigger the Ka. Usually we don't talk about the Ka, which you can in terms of acidity. Usually we talk about pKa, which is the negative log of the Ka. The smaller the Ka, the more acidic. And so if we kind of look at this equation, the more acidic something is, the more of this you make, right? And when we think about acidity, then what we want to think about is the more stable the conjugate base here, so the more stable this is, right, the more acidic this is. And there are basically two things that will stabilize an anion. Inductive effects, so putting electronegative atoms around that anion or near that anion, and resonance effects, being able to draw resonance structures of that anion. And then the third thing is solvation will also make A minus more stable. But the thing to take home here is if I ask you, if I want you to think about how acidic this is, we actually are thinking about how stable the anion is. And so when we think about this, we can start to see that the acidity of alcohols, they fall in this range of about 16. So ethanol, which is a very common alcohol, its pKa is on the order of 16. Butanol has a higher pKa. And the reason is because it's harder to make that anion, right? That proton's a little more hindered, so it's harder to get to that anion. And then if we look at methanol, this is slightly more acidic. There's not as many alkyl groups here. And water falls in between methanol and ethanol. So when we say, we call alcohols like this, we call them aliphatic alcohols, to mean that they're just alcohols with a normal alkyl chain attached to it. And so aliphatic alcohols, they fall in a pKa range of 16. The more hindered the hydrogen is, the higher the pK, the less acidic it is. Now notice that if I take some of those hydrogens on the neighboring carbons and I replace them with fluorines, I drop the pKa by an awful lot. And the reason is because the anion, so if I make the anion here, and then I remove this proton, and I make the anion here, this anion is more stable than this anion because the fluorines are inductively pulling the electrons this way. It's spreading that charge out. Now notice that when we get into phenol, all of a sudden the phenol becomes way more acidic than ethanol, right? And the reason phenol is way more acidic is because if I look at the anion that I form, if I look at the phenoxide anion I form from phenol, that anion is resonance stabilized. So this is the alcohol, this is the anion here, and I can draw numerous resonance structures moving those electrons around the ring. And so that's what that anion would look like here. Okay, and I can draw other resonance structures. So because this anion's resonance stabilized compared to ethanol, which I can't, so in the ethoxide anion, I can't draw any resonance structures, but in the phenoxide anion, I can draw multiple resonance structures. And notice also that if I look at different types of phenols, that the anion of this phenol, which is of paramethylphenol, which looks like this, right? And the anion of nitrophenol, which looks like this, right? So this paranitrophenol is much more acidic than phenol or the paramethylphenol. And again, we can explain this by kind of the activating, deactivating effects of these groups. Alkyl groups are activating, so it's trying to push electrons onto the aromatic ring, but that's not as favored for an anion if I already have the negative charge here. Whereas the nitro group is electron withdrawing, so it's pulling inductively and by resonance these electrons down toward it, making this anion more stable, making paranitrophenol more acidic. So again, simple alcohols are about acidic as water. Alkyl groups make the alcohol weaker. The more easily the alkoxide anion is solvated by water, the more energetic, so the more acidic it is. So for example, this molecule right here is less able to be solvated by water, and also this proton is less available to be removed, making it less acidic than something like methanol or ethanol. All right, so I hope that made sense in terms of the physical and some of the chemical properties of alcohols. And so the next thing we're going to look at is how we can make alcohols and how the various ways we know how to make alcohols. Thanks. Let me know if you have any questions, and have a great day.